Diganta. So we'll wait for a few minutes. Hello?
Sure. Yeah, sure.
Huh?
Yeah, sure.
Okay. There are only a couple of people here today. Hopefully there'll be more. I know a couple of people have taken permission for the puja holidays. Yeah, I mean, CMI doesn't require attendance. Attendance is not part of the requirement. But now if I record it, there's probably even less incentive for people to attend. Although people here, they have, when I asked them early on, you guys told me that you prefer physical class online. But the attendance is... Yeah, I don't know. I mean, here, two people asked me explicitly that they won't be able to make it. But yeah, that could be the reason. But even outside of that also, I feel like
Meeting is being recorded.
here, because okay, I need this. Okay, so this is kind of the criteria that I'm using for grading the paper presentations. Okay. So it'll be, I'm thinking, you know, I'm graded on two broad category. One is I'm going to test you on how well you've read the paper. That is, how well you've understood the paper that you know, you're supposed to read and present. The other one is, of course, the quality of the presentation itself, the structure and quality. And you know, I'm giving a little bit more emphasis for to make sure that you have understood the paper. That is for 60%, and quality of presentation is 40%, which is also something that you would like, you know, so through this experience for you to get, you know, get some exposure to do that. So how will I evaluate technical understanding of the paper? So this is where I'm drawing. See, that's why I made it a point to assign mentors. Okay, I don't know how many of you, despite my repeated requests and pleadings, I don't know how many of you have really taken the initiative to get in touch with your mentor. I know that I'm mentor for 4 people. 2 I approached and then I'm pursuing. They did get in touch with me. Nobody else has gotten. So I encouraged the mentors to actually go or, you know, remind you and then initiate the thing. But in any case, this is how I'll do. So one way is you can discuss, you can demonstrate how you have understood the paper through your discussion with the mentors. Okay, so their bandwidth on my request, you know, they have been made available. Okay, so these are the four things that I want you to try and understand when you read the paper. Usually the papers are papers that are published in good conferences, and they are structured reasonably well. They are problem statement, technical approach, the results of the paper in some cases, if they are both combined theory and experiments, exploration, and some future directions that based on the limitations of the approach and so on. So these are the things that I'd like you to understand, and that will also be what you will be required to present. Now, if you choose to discuss, avail of the bandwidth that the mentors are offering you, then I will, consult the mentors. But if you choose not to, if you ignore the mentors and want to do on your own, then how much you have understood will be purely based on your presentation. If you screw up your presentation, zilch, okay? You will not get an opportunity to do it. Because sometimes you could have understood the thing, but your presentation, if it is poor, then you will not, if you, through your presentation, if you're not able to demonstrate, we are not going to put the extra effort to ask you and so on. That's why I'm giving you this opportunity. But if you choose to punt it, okay, and not bother to discuss with your mentors, despite my repeated comments, that is your choice, okay? So that's what I want to make it very clear. Between now and whenever that I have scheduled your thing, you will have to take that initiative and do it, okay? Now, well, I gave you the chance of going through the paper and coming back. If you're not comfortable with the material and the topic, that date is gone, okay? Now you're stuck with whatever paper that you have. You have no option of backing out on that, okay? That's it. And that is that. And the quality of presentation is also going to be, I think that is once again where you can, if you choose to, take the help of the thing by, I will try to give you a general template, okay? That if you could use, or you can throw it away, okay? That's up to you. Okay, this is a free world, democracy everywhere. So you can do whatever you want, okay? But I will do my bit. So I will not have that on my conscience that I have done from your thing. But if you guys choose to ignore, that is your problem, okay? And then that's what, so if anything, and if you choose to read this and do it, you can come back and ask me questions. But track record, if I have to go by track record, I don't think you will ever, you probably don't even care about this and don't even read it. That's your problem, okay? So I've done my bit. And I will upload it, I will store as a link, okay, in the Google Sheet. And if you choose to read it, you are okay, I'll make you a presenter, Diganta. Okay, you're on. Diganta? Okay. Yeah. I think you're on mute. Diganta, you're on mute.
Yeah. Yeah. So we were talking about deep poly last time, and we went through this example. So any questions about this so far?
Yeah, there's no question here.
Okay, good. So yeah, so now let's talk about this. A few sort of directions in which one can go from here. One is, of course, so far we have seen fully connected neural networks with ReLU activation functions, right? But that is not the only kind of neural network out there. There are other kinds of connections, but even before that, I mean, all kinds of connections are mostly linear, so you can handle them in exactly sort of the similar way. But even before that, there is, other kinds of activation functions which are very different from ReLU in very sort of fundamental ways, right? So one of the things that the deep poly paper, so this is from deep poly itself.
Yeah, I haven't uploaded those papers, but I should do that. Maybe you can flash the references at the end.
Oh yeah, I have the references at the Intel Flash. Yeah, so this is from deep poly itself, which I think is reference number.
Yeah, I think these papers are listed in the list of papers. Okay, the list of papers that used for deciding for selecting the papers for presentation. I think it is there, but nonetheless, I'll download these things and upload links to the paper into the Google Sheet, which is my master resource anyway. Yeah. Okay.
Okay, yeah, thanks. So yeah, so this is so there are other kinds of activation functions.
Yeah,
And
I'm
this,
assuming you will explain as to why moving from ReLU to other activations require you to tweak the approach. Okay.
yeah. So on that point, I mean, see, so far what we have done, this is actually sort of specialized ReLU, right? So linear things can be handled because anyway that is substitution, like I've mentioned over here. But this sort of selection for upper and lower bounds that we've chosen, right? Where we're saying, oh, let's for the upper bound, let's just connect this point and this point, and for the lower bound, let's just we have two options like this. Let's just choose any one of these two options. See, this sort of an approach is kind of specific for ReLU, right? If I give you some random function that looks like this, you can't say that, okay, I'll connect upper and lower bounds here and here and expect to get some sound upper bound, right? So it's not immediately clear that this sort of an approach that,
Diganta, just to test the knowledge, okay, I'm going to ask a question, okay?
Sure.
Just to keep no, he showed, why is it, what is wrong with connecting, taking 2 points like that he has shown there, and then taking that as the bound? Jessica, can you answer that? I'm sure you won't be able to answer it because you never attended any of the previous lectures. Or have you even listened to, taken the time to listen to the thing? No. I don't want any excuses. I just say yes or no. So you won't be able to answer. So whoever, I mean, I'm not surprised. And I'm sure that you are smart enough to go and listen, and then you will be able to answer. But you have also learned about over approximations and so on, not just in this course and other courses as well. And you are, fully knowledgeable about it, and you will be able to answer that. But do take the time to listen to the lectures, and because there'll be assignments on using for you to use DeepPoly and other tools that we'll be covering here. Anybody else? How about you, Anuraj?
I'm not sure, but the curve kind of crosses the straight line at that point. That is not acceptable. So it's kind of over approximate, right? So it's not
Yeah, I think
over.
you have kind of the idea that is correct, but yeah, yes, you are getting that. That's not a sound over approximation.
Yes.
Yeah, I mean, the line's supposed to be an upper bound for the function, and yeah.
Right.
So yeah, so there are areas, which is what you were getting at. So you got the idea. So which is, some things that had to be included are not there. Okay, so that is why it's not a sound over. It's not an over approximation. Yeah, that's
right. So in fact, just to make things even more clear for people watching. So if I had taken these two lines as my bounds, for example, here, right? Then what am I saying? I'm saying that the values that I'm keeping track of are all of the values here. Now that of course covers all of this part of the curve. But then there are values here that the actual network can take, but is not getting covered. And similarly over here as well, right? So for this reason, this is actually not a sound over approximation. Or in other words, this is not a valid upper bound because here is a amount by which it is deviating.
Yeah, you can go ahead. Diganta?
Okay, yeah. So this is what we had for ReLU, right? But like I'm saying, it's not very trivial to extend it to other functions necessarily. And this is the theme that we will see few times with respect to this slide deck, and also what is supposed to be the next lecture. What was supposed to be the next lecture on Linsin actually narrows down on this problem and really tries a lot of things to try and solve this problem, like, of general activation functions and what do you do in that case. But for the purposes of this paper, in this paper, DeepPoly, they actually talk about ReLU, and then they talk about extending it to a few other activation functions. They don't propose anything general enough to handle all possible activation functions, but they do extend it to a few other activation functions, right? And the assumption that they make about their activation functions is that it is, first of all, increasing, and it is convex below 0. So this region, it is convex, and then above that, it should be concave, right? So this is a sort of assumption that they make. And a lot of the classical common activation functions like sigmoid and tanh are actually do belong to this sort of a class. So of course, sigmoid and tanh were I think sigmoid and tanh both were sort of the first class of activation functions that people tried even before ReLU. Even before ReLU became most popular. But yeah, both of these are in this class. And this actually allows them to, so whatever they do will work on these two functions in a similar way, and also any other function that satisfies this kind of a property. Now,
there's a question here.
Yeah.
So identity yourself.
Yeah, I'm Avik, and yeah, so what is the DeepPoly of 5 that you have written?
Oh, so this is just reference number 5. I thought I'll just put the references. So down here I have some list of references.
5 of DeepPoly as well. So I think that's he is referring to the reference number.
Yeah. So this is the paper. I just put all the references down here, and this is, in reference number 5 in this particular slide deck. I don't know what number it has on the list of papers, that the common list of papers, but at least in this slide deck, it's left reference number 5.
Yeah, I think you don't need to worry about that.
Yeah.
I will upload as I Yeah, with links there.
Okay, sure. Thanks.
People who want to take a look at it
Yeah,
can do so.
sure. So okay, so then yes, then we have this sort of a function, right? Again, so if you remember in the ReLU case, what we were doing was we were basically taking three cases, right? One when it's entirely negative, one when it's entirely positive, and then the general case where the lower bound is negative, upper bound is positive, right? So similar sort of a thing is being done here. There is a situation where the interval is entirely positive, right? So if the interval is entirely positive, what do? We connect the endpoints for the lower bound, not for the upper bound, but for the lower bound. Now, can anyone tell me why this will be sound? Just a one-line argument as to why this should be sound. Why can we do this? I just use some example where this connecting endpoints didn't seem to work, but it does work here for the lower bound. Why is that the case?
Yeah, because the curve only lies above that line because it's
Yes.
yeah, plus axis quadrant.
Yes, exactly. So that is precisely what it means for the curve to be concave. So by definition of the curve being concave, it will be above any sort of chord joining 2 points in the curve, right? So that is why you can take a lower bound by connecting 2 points here. And similarly, you can do the opposite thing for the negative side interval, any interval entirely in the negative side. You can connect the 2 points and that will give you a sound upper bound. Because again, the curve there is convex, which sort of by definition means that this, if you join these 2 points, the line that you get will be an upper bound. That is sort of the geometric definition of convexity, right? So this is good. But then what about the upper bound in this case or the lower bound in this case? We have not said anything about that, right? And also, of course, what happens when the interval looks like this? Again, we have not said anything about that yet, right? So what can we say in that case? So in that case, see, what we realize is this other observation about functions of this form that they make, which is that the slope of the function is minimum at one of the ends of the interval, right? So what does that mean? So let's think about a function that looks like this and think about what its derivative will look like, right? So the derivative of something like sigmoid actually looks somewhat like what I've drawn over here. But why is that the case? Let's try to understand this a little bit better. See, here, firstly, the function is always increasing, right? So that means the derivative is always going to be positive. So that is there. But the derivative, so the function is convex below zero. So convex, the other definition, equivalent definition of convex for doubly differentiable functions is that it means that the derivative should always be an increasing function. And I should probably mention this, that most of their analysis works for doubly differentiable functions. Yeah. So most of the analysis, yeah, works for this kind of things. This in this sort of functions, the equivalent definition of convexity is that if you are in this sort of a region, the slope of the function will increase, right? So the derivative, if you think about it, so that is what it means to be convex, right? Like the second derivative is positive, which means the derivative will increase. And finally, at around zero, it will hit some maximum point. And then after that, it will start decreasing, right? So this is what the derivative will sort of look like. So just excuse me, can you give me just 1 second? I'll have to just I'm sorry about this. Just give me 1 second. Yeah, excellent. So this is what sort of the derivative looks like, right? So if the derivative looks like this, now consider any sort of interval over here. And this can be either entirely positive, entirely negative, or in both the regions, right? Doesn't matter where it is, but if you consider any interval, see, since this function increases and then decreases, if you consider the two endpoints in the interval, one of them will definitely have the minimum value within the interval, right? In this case, it's this point, right? Similarly, if I taken such an interval, this endpoint would have had the minimum value, right? It will never be the case that the minimum value will be achieved somewhere in the middle of the function, right? So it's never going to be the case that you'll get a minimum value some of the derivative somewhere here, because it's going to increase from this point onward, and then eventually it might decrease, and it might decrease to below this point, but then again that is the minimum value is going and it's going to be hit at this point, right? So if that does become the minimum value, it's going to be at the other point in the interval, right? So the minimum value will always be at one of the two endpoints of the interval, right? So based on this observation, what they sort of say is that since the slope achieves the minimum at the ends of the interval, they say that, okay, look at the two ends of the interval, find out the minimum slope from that. And in the case where things are positive, you can take the minimum slope and start with the rightmost endpoint and draw a line. And that will always be a sound upper bound, right? Why is that the case? Because if you start from here and start moving in this direction, see the function, according to the value of this slope, the function always, as you move towards this direction, the function will always decrease at a rate faster than this line does, right? So the function will always remain below this. Similarly, for this case, you can take the maximum slope and start at this point, right? So the minimum slope and start at this point, right? So again, the function is increasing here, but it is increasing at precisely the rate at which this line is increasing at this point, and it will continue to increase at faster and faster rates over here, right? So it's never going to come back and intersect this point. And now in the general case, what do they say? In the general case, they say that, okay, find the minimum slope and then draw two lines from the lower and upper bound from that particular minimum slope, right? So again, why does this give me a sound upper bound? Because this is the minimum slope, and whatever the line does, so this can maybe be proved well with using an integral. So this is the minimum slope, right? So in some sense, sigma prime x is always greater than this line. Let's call this line alpha, right? So what is the value over here? The value over here is can be given by the value at this point, which let's call it sigma of u minus the integral of sigma prime between these 2 points, right? Integral from x to u of sigma prime x dx, which is again less than equal to integral x to u of alpha dx, which is basically, maybe I should say t here, which again is basically just equal to u minus x times alpha, right? So we have sigma u minus x times alpha, right? So then this is the line x times alpha, or plus sigma u minus alpha times alpha, right? Which is precisely this line, correct? So the general idea, I mean, I solved it via some integrals, but the general idea is that if you start with the minimum slope, whatever the change that is achieved by your function, that change is going to be at a rate that is going to be faster than the minimum slope, right? So from this point, the function is going to always go down faster than this line is going to go down, because this is the minimum slope that you have. So the function is going to go down faster than this line. And similarly, at this point, the function is going to go up faster than this line because again, this is the minimum slope. The function never sort of slows down to a rate of increasing that is less than this particular line, right? So this is the sort of heuristic, if you will, that they follow for functions of this kind. Any questions about this?
Any questions? Yeah. Yeah, there's a question here, by.
Yeah.
Could we not do much better by trying to find a line parallel to the 2 points which we joined for the other bound?
So
I'm
you're
saying,
saying
suppose
let's
we want to
try,
find the upper bound. We already have a line for the lower bound.
right?
If we
And
try
here
to-
you're talking about which case? Are you talking about case number 1, 2, or 3?
so for example, for one,
Okay.
we have the lower bound. For the upper bound, if we just try to find a parallel line that does not, if we sort of just
Correct,
try,
correct. So you're saying that let's try to find some line like this, right? Is that sort of what you're saying?
yeah, sort of.
Yes, yes. Of course, you'll have to formalize the soundness argument, but yes, that can be done. That might give you something much, much better. And other papers, for example, Crown itself, which is there in this particular slide deck only, the Crown itself has traveled something along that line to get a slightly better bonds.
Sir?
Yeah.
So you said the line goes at a lower speed than the curve itself, like
Yeah.
like it decreases at a lower rate than the curve. What does it mean for a line to decrease at a lower rate than the curve?
So what I specifically mean is that if you look at the line itself as another curve, right? The
Yeah.
line itself as, if you look at it as another curve, it is just a curve which increases or decreases at a constant rate, right? So for example, if we take this line, as we move this way and move a point along this way, the value on this line will always reduce by whatever that slope of the line is, right?
Yeah, I get it. Yeah.
Yeah. And the value on the curve, see, because this line is the line where the slope of the line is also the minimum derivative of the curve, the value that you take along the curve will reduce at a faster and faster rate, moving away from the line, right? So if you're not convinced by this, like I said, that you can actually take an integral and prove this. This is what they do in the paper. They don't make some sort of a visual argument or a geometric argument like this. They actually say that, okay, take the derivative. Now we've chosen a line so that the derivative is always greater than the slope. And then from this sort of an inequality to derive a bound on the actual curve, what do? You integrate sort of both sides, right? So then, what you get is this kind of a thing. So this is actually equal to sigma of x, right?
Yes, sir, I understood.
Hello.
Yeah.
Diganta. Yeah.
Yeah.
So I have one question. So we're bounding it by the slope, right?
Yeah. Yeah.
Yeah. So my point is, suppose the slope is so there is a so in the diagram 3 there is a black point, right? In
Yeah.
the slope, in the function. So if we take the slope there,
Here you see?
yes.
Yeah.
Then how is it like bounding the other things? Like
No,
so-
then it won't. Then it won't, right? So the point is that we need this sort of an inequality for the slope, right?
Oh,
And
okay.
to get this inequality, we would have to make sure that whatever point or line that we're picking, the slope of that line is actually always less than the derivative of the curve, which means we have to pick a line where the slope of the curve is minimum, right?
I see. I see.
So that is why we're picking actually the slope at this point here.
I
right?
see.
And the reason that we can actually pick a line where the slope is minimum very easily and quickly, we don't have to go searching for it somewhere inside the interval, is because here we know that this function is convex below zero and concave, which means that the derivative is actually itself always concave, which means that the minimum will be either in the leftmost point or in the rightmost point on the interval. The minimum will never be somewhere in the middle.
I see. I see. I see.
Right? So all we need to do is look at the slope at those 2 points, find the minimum value among them, and then choose that as the slope.
Okay, I get it now. Yeah.
Yeah, but can you be clear? I don't know if this confusion is there. So what is the overall L and U for this case?
So the L and U,
Is it divided into two, the negative and the positive portions, and then you give different L and U based on the slope?
no. So first is the L and U. So maybe I'll just go back a little bit and recap this. So if you remember, even in the ReLU case, or this is actually general sort of way in which they do this. There is this Li and Ui that we're keeping track of as part of our abstract domain, right? Which are the concrete bound. So along with saying that for this particular neuron, we will have some linear upper bound and some linear, some linear lower bound and some linear upper bound. We're also going to say that, okay, along with that, in addition to that, it is also bounded by these concrete values, right? So now when we try to find the linear bounds for the output of the ReLU, what do we use in the ReLU case are these concrete bounds for the input of the ReLU, right? So here, for example, what we're saying is Z is ReLU of X, and what we know about X is that it is always in this interval. Then given the fact that X is always in the interval, what can we say about Z in terms of what is a linear upper bound for Z and what is a linear lower bound for Z in terms of X, right? So we know X is in this interval, which is given by Lx Qx. Then what is a upper bound for Z, which is given by ReLU of X, or a lower bound for Z again, Z being given by ReLU of X. This is the setting that sort of we have, and that is what the value of element.
So analogously, how is it done there?
So analogously here also, what we're really saying is, so let me maybe write here, is that we have some more complicated activation function, let's say sigmoid or whatever, right? So we have Z is equal to sigmoid of X, right? And this axis actually represents my X values, and then this curve or this axis is my Z values, and then this curve is the sigmoid of X, right? And then what are we saying? We are saying that this Z, what we know about this Z from all the propagation that we have done so far, we have some set of abstract values for Z, right? Which is some linear upper and lower bounds, but also we know that Z belongs to some concrete upper and lower bounds, right? So we also know this fact about Z. And then given this fact, we are trying to find, sorry, I meant X. So yeah, I meant X. Yeah. So we know some concrete, so we know some linear upper and lower bounds for X, but also we know some concrete linear upper and lower bounds for X, right? This is something that we already know from all the propagation that we have already done so far. Now, given this fact, we're trying to find some linear upper and lower bounds for Z, again, in terms of X, so that, it is actually an over approximation with respect to whatever this function is. It is exactly the same as whatever we had in the previous setting. It's just that this was ReLU. Now this is something a bit more general.
So based on that, you were doing it. If it's either L and L1 and the L and U are either on the positive or on the negative, completely on the negative, then you choose that based on the slope, is what you're saying.
Yeah,
right?
yeah, exactly.
But what if the L and U are, L is on this side and U is on the other side?
Yes, so that is the case number 3 that I've drawn over here. So maybe let me just erase or move this calculation, just move it to the previous slide. That is, maybe I'll just make it a little bit smaller. So that is this case where this is the case that represents that situation, number 3. So there, what we're doing is we are going to again find. So this sort of 3 steps. Let's say. So let me maybe duplicate this and save it. Yeah. So there's 3 steps. So step number 1 is to find the minimum slope. By slope, I mean derivative of this thing in L and U, this interval, right? And this can be done easily because we know that this will either happen at L or U, right? So it is either this or this. And we just need to compare these 2 things and choose the smallest among these. Nothing else in the middle of the interval can ever be the minimum slope. Why? Because sigma prime of x itself is concave because of this condition. So this actually implies this, right? So if it is convex below 0 and then concave, that means what? Sigma prime increases and then decreases, which means sigma prime itself is concave. Which means if you pick any interval, the minimum value of sigma prime will either be at one end of the interval or the other end of the interval, right? So this first step of finding minimum sigma x can be done easily by just looking at the 2 ends, right? So now what do we have? We have so we have a situation where we have some interval LU over here. This is again sigmoid. And what do we know? We know that for values of x within this interval, we know that the derivative is always going to be less than this. That means we already have a slope of a line. So we already have some slope of some line like this, so that we know that the values in this function don't change faster than this line, right? So if we now drop a line parallel to this from this endpoint, then this will always be an upper bound because the values along the black curve, they will always change faster than this line. They don't change slower than this line. So the values along this curve will always change faster than this line, which means that they will always decrease faster than this line, which means they'll always fall away from this line. They'll never intersect back. For this black curve to go back up and intersect this line, somewhere the values has to increase faster than this line, which is going to contradict this condition, right? So that is never going to happen. Similarly, if we start with this point and again take the line parallel to here, again the value is only going to increase faster than this one, right? So again, if we had a situation where this curve somehow curves back and hits here, then somewhere the value would have had to decrease or increase slower than this line, which is again going to violate this condition that, you know, the slope of this line is actually the minimum gradient of this curve, of this black curve, right? So again, that can never happen. So again, this will be a sound lower bound. So this is basically what we use.
Here, but I guess Romit's question is still there, no?
Sorry, can you repeat this question? I think.
No, he's saying that why use parallel to the.
Oh yes, definitely. It's not at all clear why this should be the best way. In fact, it is not the best way. It's
not the best thing. But I guess there will be some tweak later on to.
Yes, yeah. Crown does a tweak. And then Deep Poly itself actually uses a slightly more general, but potentially slightly worse set of bounds, but they stress more on the generality. And then Linsin tries to actually do a lot of work to get the best possible bound in the most general setting. So we'll see sort of all of these variants.
Yeah. Okay, so that you will cover when you talk about Linsin later on.
Yeah, I will talk. Yeah.
Yeah, that uses, by the way, I guess I'm giving the punchline out. So some SAT solving technique, right?
Yeah.
Yeah. So whereas in Deep Poly, they will just do it very crudely like this, or do they have some way of doing slightly better than these?
No, this is exactly what they do.
Oh, this is what they do. Okay.
Yeah. So this was sort of a first proposal kind of a paper, if you will. Both Deep Poly and Tron, and this is precisely what they do. Crown does something slightly different, which may be better in some cases. But again, it's only slightly, and this is what they do. Yeah. Yeah, so this was this case where we have sigmoid and tangent. And now the other kind of activation function that they actually handle is max pooling. Any questions before I go into max pooling?
Raj? Okay. No questions. Yeah.
Sure. Okay, so max pooling again is sort of handled in some, like basically they again have some sort of heuristics, right? So again, okay, first thing I want to point out is that for max pooling, and I don't have that written down somewhere in the slides, unfortunately, but I think I should make a note of this. This is actually a multivariate activation function, right? So it is not an activation function in the sense that, it is just like ReLU or sigmoid or tangent, where it's taking a real value and giving you another real value. It is a multivariate activation function, right? In the sense that it's going to take in multiple values and then give you a single output. Nothing in the rest of the framework that we are working with changes because of this. Because at the end of the day, what we really want again is even if we have some multivariate activation function, so this is multivariate. Nothing changes because of this, because again, what is it? What does that really mean? That means that we have some linear here, and then there's this box, and then there is some linear here, right? At the end of the day, all that we want is for each output of this box, we want a set of linear upper and lower bounds in terms of the inputs to this box. Now, it turns out that if it is not a multivariate function, if it's a univariate function, so let's say that the inputs are x0, x1, x2, and x3, and the output is z, or z3. If it is the univariate function, then, what we always can find and end up finding, in fact, is some bound of z3 in terms of just x3. So we'll just say x3 times some alpha 3 plus b less than equal to, so let's say that is for lower bounds, and x3 times some alpha u3 plus b, right? So this is actually a linear bound, which is only in terms of
I'm confused. I don't know if the rest of you are. So, but in a normal DNN, you never, what feeds into the output of the linear layer is a single thing, nah? So why is it multivariate at all?
Yeah, so no, the normal DNNs, if you only consider univariate functions, it will be univariate, but
yeah,
the max pooling activation function is actually not a univariate function. So that is sort of a deviation, if you will, from
pooling is a slightly different kind of.
Yeah. So it is actually used in CNNs. So the main sort of, there's nothing preventing one from using it in a normal DNN as well.
Okay, so I don't know. I haven't make a note. So it's used in CNN. Huh?
Yeah, but again, if people are not entirely
use multiple windows and so on.
Sir, could you demonstrate an example so that I can understand the difference between this multivariate and univariate?
Okay, yeah, sure. So I'll make a bit more sort of clear example. Yeah, maybe I should have stressed on this point in the flow of things, but yeah. Okay, so
You have to give an example of how multivariate.
differs from univariate. Yes.
Yeah, I mean activation function. Yes.
Yeah. That is what I'm doing. So let's consider this sort of a case, right? So this is your normal univariate sort of situation, where what do you have? You have some linear layer, and then notice here that you're taking one value to one value via your activation function.
Yes.
Right.
Yeah.
And then whatever, we have some other linear layer, which is actually not entirely important for us, and maybe not even going to draw that. Right?
That's fairly clear.
Yeah. So let's now say this is x0, x1, y0, y1, z0, z1. Right. So as we propagate things, what will we get? So when we propagate through the so when I say propagate, I mean propagate the these abstract values. When we propagate through the linear layer, we will get some bounds of y0 in terms of x0 and x1, right? So we'll get some bounds that looks like x0 times some alpha 0 plus x1 times alpha 1 plus b. Y0 is greater than equal to y0 and so on, right? And I'm only drawing one side, I mean only writing on one side. And similarly, we will get this sort of a thing for y1 and so on, right? And then when we come to z0, so what will we get for z0? So if you remember what we had been doing in the example, and before that when we were talking about propagating through the ReLU and so on. So if you notice here, for example, for x5, the bound that we have is just in terms of x3, which is this guy, right? It doesn't actually involve x4. And it doesn't need to involve x4 because there is no dependency between x5 and x4, at least not directly, right? So because of that, this bound doesn't need to involve anything in terms of x4, right? It is only going to involve x3. And then, of course, you can substitute x3 back in from here. But if, like, a priori, it is only going to involve x3. It's not going to involve anything else from this layer, right? So that is the univariate case where
that part is okay. Yeah. So whereas in the max pooling thing, they the activation functions will end up using
multiple variables. Yes.
And why is this relevant for CNN? Why you say that this is used for CNN? I mean, maybe you can cover that.
Yeah,
okay.
yeah.
For the purpose of this talk, let's assume that there are functions like that. Okay. Go ahead.
Yeah. I mean, I can quickly say sort of
motivate that.
Yeah. So I think whenever we have an introduction to CNN, that might be
CNN as well.
Yeah. So whenever we have an introduction to CNN, that might be a good place to.
You go ahead. That was just a digression. I was giving Jessica a little bit tough time here.
Okay, sure. Yeah. So in the multivariate case, this is basically just going to, I mean, I'm not redrawing the linear layer, but then here we're going to have some max node over here. And this max node, what is it going to do? It's going to take the max of y0 and y1.
Preserving it, and you're leaving it. He's gone.
Sorry?
Go ahead, Diganta. This is some joke that I'm doing.
Oh, okay. Yeah. So this is what, like, because this node now involves these two things directly. Of course, if you want a linear bound for this node now, such a linear bound should involve both y0 and y1, right? So it will have some y0 coefficient, y1 coefficient, and so on. This is all I mean by the multivariate case. Is this clear to everyone?
What complication will that introduce?
So in the large scheme of things, nothing, but just that right now, when we want to extend this thing to the max pooling function, we have to remember that the linear lower and upper bounds that we calculate, because z is equal to max of x0, x1, and x2, it should be a linear lower and upper bound in x0, x1, and x2. It should involve, ideally all three of them right? So it is going to potentially be a linear lower or upper bound.
So
in
it
terms
has
of
to
what-
use the linear upper bounds of all those three variables. correct?
Yes, I mean, ideally it should, right? So
Yes.
the heuristic that they use turns out that it does not, but this is sort of the setting that, right? Okay. So yeah, so again, we have three variables feeding into our activation function right now, right? It's not just one variable, and these three variables are in these three interval sets, right? So this is the first case where one of these intervals is clearly the lower bound is actually greater than all the other upper bounds, right? Which means that the max will always be locked into selecting this particular variable, right? So the value of this particular variable will always be greater than these two. So the max will always be selecting the value of this particular variable, right? So in this case, the max actually reduces to z being equal to x, and that is what we capture in our linear equations. Okay. This is the special sort of case. And in the general case, what we have is we don't have some interval which is dominating every other interval, right? So what do we do in this case? See, in this case, we could have actually, if you consider any of these x0s, x1s, and x2s, any of these, by definition of max, actually forms a good lower bound for z, right? So we can take any xi and say xi is less than equal to z, right? So for any xi, this sort of an equation works, correct? So in some sense, the choosing this max is about choosing some. So what these deep poly people do is that they say that, okay, then choosing the max is about choosing one particular I here, and then saying xi is less than equal to z for that I, right? So they choose the I for which this lower bound is the largest, because then, you know, if the lower bound is the largest, then that is got the largest chance of being the value that actually dominates, which means that if you choose that I, then this equation has the largest chance of actually being tight, or being equal. This inequality has the largest chance of actually being equal, right? So this is the sort of motivation and heuristic that they use for the lower bound. Just choose that particular xi which has got the lowest one, and set up the equation in this way. And then for the upper bound, they actually end up choosing an interval upper bound. They just choose the largest upper bound as the upper bound, right? So in fact, in their case, these three things, none of them actually come into the picture, right? None of the actual variables come into the picture. This is a constant value. It's not
seems
even a
quite,
linear.
reasonable, but I mean, is there a way to do it better than this?
Much better, yes. It is very possible to do much better, and that will become a relevant discussion where we talk about this Linson paper.
I see.
So again, this is just sort of a first stab, if you will, and for that it is.
So this max pooling activation function, does it always take the max of these multiple variables, or can it use other functions as well?
No. It is max pooling is by definition always
It's always max of
yeah.
that. Therefore, you will have to get the best of it. Okay.
Yeah, it is actually possible to do much better even for max pooling. I mean, even for max pooling, yeah, I mean, it's very sort of clear that this is not necessarily the best one, and we'll see more of that.
Okay, go ahead.
Yeah. So then, yeah, this is the point that I think we've already sort of made, which is that this is not very tight, not for max pooling, not for anything. And I have mentioned 3 papers which we'll discuss.
Yeah, what is our plan? Maybe you should mention here what's our plan for covering. How much do we plan to? How much?
Yes. So right now I plan to cover Crown and Linson at least. We can maybe even cover 3, or we can drop 3.
That I don't know. I mean, I'm still okay. Crown and Linson certainly will cover, and I think, I mean, the idea for me is, guys, I mean, these are internal to these tools. Okay, so while I mean, I will have an assignment where you will get some hands-on experience. So you already, it's a digression I'm taking.
Yeah, sure.
Permission. So you already have a small example in which you have done Z3. Okay. I'm going to have you do something similar, the same or something similar using Marabou, okay, which was covered by the node merging abstraction that Madhukar presented. Okay. I mean, the idea is, and he's doing deep poly and will be covering Linson and Crown. So all those things, these are bound oriented thing, whereas the other one is general predicate. So hopefully you will, after listening a little bit into the techniques and what they're, to give you an idea of what the limitations and strengths and limitations are. These things scale better than the node merging tool, Marabou. Yet they have their own limitations, like they are over approximation in different ways. So what I'm hoping to do is to have some examples that show that exploit or the strengths of these tools, or expose the weaknesses of these tools through those examples, which is what eventually I want you guys to be doing, so that you will get hands-on experience on the tools. But at the same time, you need to know a little bit about the workings of these tools, and that's the thing. So how do you do? So you have half an hour today,
Yeah.
and one more lecture, okay, if you want to stick to our schedule.
Yeah,
so
yeah.
You'll be able to do, I mean, Linson itself will take one, okay, and then Crown, maybe
The
two
Crown, I
lectures
think Crown is not much is there beyond this. So Crown, I'll be able to cover it today itself.
Okay.
Hopefully in the next half an hour. Linson is, there's a lot of
Linson
things.
is good that you will have to definitely cover now. Yeah.
Yeah. I mean, Linson is an interesting sort of technique. But then for alpha beta Crown itself, there is few more things left there. There is alpha Crown, which is talking about the gradient descent aspect of things. And
see, I definitely want them to go away with having used these things on examples. Okay. That I definitely want to do. I mean, no matter how much we try, because we will need a lot of thing to cover all the nitty-gritties of Linson and alpha beta Crown, right? So you will have to use your judgment as to covering the essential ideas, and then have either Shauriyam will do in a tutorial as to how to use these tools. Okay.
Yeah. Sure.
So the usability aspect and how the interfaces, etc. I'll have Shauriyam do in a tutorial. So use your judgment. You have today half an hour and another lecture to cover whatever you want to cover on Linson and Crown. Yeah.
Okay. Yeah. Sure. Yeah. So given that, I think so at least it be covered.
You have a slide there about deep poly performance. You want to maybe you should cover that. Yeah.
Yeah. Yeah. So yeah, like this is not necessarily very tight. Okay, so regarding deep poly performance, I mean, I have set up some slideshow kind of thing, but anyway, we'll go over the points. So first point that I want to mention is that this is incomplete verification, right? And the point is that deep poly itself, alpha beta Crown is a complete tool, but deep poly.
You understand now why it's incomplete? So as opposed to Marabou, because there's a refinement there. Okay. So whenever you do verification with over approximation, that point he made, I mean, Diganta in the beginning. So if it says no, it's not verified, you don't know. I mean, because it could be due to a spurious counterexample and so on. Unless you make it more precise by reducing the imprecision of your over approximation. That's what refinement does. Whereas Marabou has refinement, this one does not. That's why it's incomplete. Yeah. So that's why it's also much faster. Whereas Marabou uses reluplex at its core, whereas here there's no reluplex, which itself uses simplex and so on. Whereas here everything is based on some algebraic methods. Yeah. Okay.
Yeah. Yeah. So this is entirely incomplete verification, which is good to keep in mind with respect to these experiments. So the idea then is that it is not may not be able to solve every query, but it is much like orders of magnitude faster than Manipur. So the queries it can solve, it can solve very, very fast. Yeah.
Another before you go to the next point,
Mhm.
another restriction of this tool is the kind of property. I guess.
Yeah.
The kind of property here is all expressed in terms of bounds of the value that you get out of at the nodes. Okay. So you're able to, so eventually if you want to state something about the output, that also has to be expressed as some bounds. Of course, the bounds can be expressed as linear expressions of any of the inputs that are the values that appear prior to the output. Whereas Marabou also has that restriction that you can only do greater than or less than. But as Madhukar showed in all the examples, you can encode. We spent some time, okay? You could encode any arbitrary formula, propositional formula involving linear inequalities as with DNN using RLL. I'm sorry, ReLU, okay? Therefore, you could put that in there and then get an extension. So the question that I have, Diganta, here, I guess, here the property which is expressed on the output node will have to be expressed as some something which is greater than or less than or equal to some linear expressions, correct?
Yeah, but I think so. The encoding.
But you can use encoding here also to.
Yes. Yeah.
Do that. Okay.
Yeah. To work around that on the output side, and of course on the input side we are a priori limited to intervals. But then again in the DeepPoly paper they also show that is not necessarily very bad, because what you can do is you can, if you have a more complicated property, you can take over approximations of the input itself.
So you can use that encoding trick here also. Okay, you
Yeah.
can encode if you have some other property that doesn't fit your pattern. Okay, you understand what I'm saying? Yeah. So because this is a usability aspect of your tool. Okay, which is important for you to, regardless of what the internal technique is. Okay, so you could encode the property beyond this greater than, less than, or equal to as a DNA, which trick you can also use here. But the kind of over approximation that is being built here is different than the node merging abstraction that Marabou uses. Okay, so it'd be interesting to compare how exactly these two things perform in terms of the expressibility. Yeah. So that is one point that I wanted to make. Okay. Yeah.
Yeah. So yeah. So this is regarding the experiments. What they really compare against is a few abstract domains. So there's some other abstract domains, right? Which is these few domains: AI squared, LIMP, DeepZ. So DeepZ uses zonotopes and FastLin and AI. So FastLin actually uses the similar sort of triangular approximation, but they actually.
You guys know what he's talking about in terms of abstract domains? No. First, so far, he illustrated all the approach using interval domains. Okay, so you could do similar things with other domains as well. I mean, can you briefly tell what these domains are?
Yes. So AI square actually has a multiple domains, including octagons and polytopes. So maybe I should even say what does that mean. So this has got octagons, polytopes, and so on. Which means again that so remember that we are basically propagating these shapes, these sets, AIs, right? If you go back to this sort of slide, we have what do we mean by an abstract domain? It is a template to come up with these AIs and the way to transform these TIs, right? And of course, this is one way of doing it, is interval domain. Another way of doing it, which we went over in detail, is actually whatever that is deep poly is doing. But beyond that, there has been several different things.
No,
that
but
people
this,
have
this
looked at.
bullet, does it mean that, I mean, in phi compared with other domains 6, I didn't understand that. Does deep poly support these?
No.
more
So
powerful
they
domains?
do an experimental comparison against other abstract interpretation domains. So AI squared is a tool that supports octagons and polytopes.
So they are not supported in deep poly, but
right.
general, like as I mentioned, software abstract interpretation based tools that are applicable to software verification in general support very sophisticated domains.
Yeah.
So they are comparing deep poly with other tools that support these more sophisticated domains
Yeah. And
for DNN verification. Okay, is
Right.
that right?
yeah, that is what they're doing. And from what I at least interpret their
So
experimental
what is deep
approach.
Z?
So deep Z is zonotope. This is
Zonotope, huh?
yeah.
Oh, I
This is again from Gagandeep and others, but this does zonotope.
Mhm.
And I think Fastlane is actually another sort of polytope domain, another variant of polytope. So the point that they try to make with all of their experiments is this sort of claim that there are all these domains, but their domain is the sort of sweet spot between being able to prove a lot of things and also being much faster than these existing domains. So
I mean, you can expect that deep poly will be faster because it uses a simpler domain.
correct, and it
But-
turns out that it's also accurate enough, which is
Oh, I see. Their
Yeah.
experience on these MNIST benchmarks, it's accurate. Huh?
yeah, and these are image classifications. So yeah, that is a good like another point to make, that this is very specific kinds of networks, which is this MNIST and CIFAR10, both fully connected and convolutional networks. If you don't know what convolutional networks is, I don't think I'll be able to cover it right now, but it's not entirely.
You guys
Yeah.
familiar with MNIST and this thing? So these are benchmarks. You are familiar. Okay. So the same benchmarks are actually used to evaluate these tools, by the way. Yeah.
So what they did was they took some trained MNIST and CIFAR10 fully connected and convolutional networks, and then they came up with this epsilon robustness perturbation properties, right? So they'll start with some input image and then add some noise, right? And if this X naught is some input image, they'll take all the X's which are within some epsilon distance from X naught under some norm. If the distance between X naught and X is less than some epsilon, then they want to show that the neural network classifies X and X naught as exactly the same thing, right? So the idea being that you start with some image and then make slight small changes, like adding noise to the image to get this X, and this noise is bounded by epsilon.
Yeah.
And if you
this
do
is
that,
the
the classification doesn't
property.
change. Yeah.
This is the robustness property.
This is the robustness property.
If you perturb your input within a certain thing, then you still get the same output. Yeah.
You still get the same output. And this is the sort of properties that they check on. On this particular networks and properties, it turns out that this abstract domain is working very well. So again, the point of this paper was to say that, okay, we have a novel abstract domain that works very well for neural networks, better than the ones that were being borrowed from program verification subsets. And the two metrics that they use to try and establish this is percentage verified. So again, the idea is that it may not be able to solve every query, right? So they, instead of saying, okay, instead of trying to solve every query, which they can't do anyway, they said, okay, of all the queries we tried, this is the person that we would actually be able to verify. And of course, they also mentioned the time. So yeah, so given this experimental setup, this is the sort of result. I have not linked their or taken a snap of their table and added it here, but instead sort of summarized the table. You can take a look at the paper for the original table. They have a lot of data in the tables. But for fully connected networks, it was significantly better on both of these metrics, right? So they were able to verify significantly more and in significantly less time. The closest runner-up was DeepZ, and the DeepZ was not that close for the fully connected ones, but it was the one that was performing best among these three in compared to um, uh, this DeepPoly. But DeepPoly was significantly more
Yeah. So
accurate
the
and
question here as to what is fully connected. Fully
Okay.
connected.
so fully connected is basically it does not have any special things like convolutional or any other sort of
But
layer.
I don't understand. When fully connected means, you can have it graphically fully connected, but you can make the weights 0, which means it's not connected. No? So how will you, what do they mean by fully connected?
Yeah. So fully connected. So there is two things. So one is that
Non-zero weight.
no. So one is that fully connected actually subsumes, technically speaking, if you think in terms of expressive power, convolutional is actually entirely subsumed by fully connected in terms of expressive power. So every convolutional network can be expressed by a fully connected network.
What
Right.
is fully connected then? Define fully connected.
Yeah, the actual, I think, better sort of working definition is during training, none of the edges, or let's say that no edges were set to 0 or were fixed to 0. So during training, all of the edges had an opportunity to get a non-zero value. If still they choose to get a 0 value, if the training converges to that, it may happen. But they had an opportunity to converge to a non-zero value during the training process. Whereas in a convolutional case, what we do is we fix most weights to 0, or equivalently, there are only a few connections. Not all possible connections are there. So this is what I think in this context they mean by fully connected. So of course they were training their own distance CFAT networks to do this sort of evaluation, right? And while training, they didn't put any extra restriction on the edges. Anything can be connected to anything, and any of those connections can have any weight. And now they'll let it train, and then it may converge to whatever it converges to. And of course, in most cases with fully connected network, although this is not strictly a definition, but most cases what happens is that all edges have some non-zero weight, even if it's very small.
So one question.
Yeah.
So by fully connected, you mean like from one layer to the next layer, all the edges are.
Oh, yes. So whenever I'm talking about fully connected or convolutional, I think in none of them they have any connection that goes across layers.
If it comes from the previous layer, it's not even a DNN. No. Yeah.
Yeah, I think there is. I think these people use a term for that which they call residual connections, and I think this either DeepPoly nor Crown I think handles that, at least not out of the box.
Yeah, but see, one other question that I had is in their experiments, they have compared DeepPoly, so benchmarks with these tools, with abstract interpretation tools or static analysis tools that support more sophisticated domains.
Yeah.
But the real comparison, relevant comparison to me, should be other verification tools, competitors like Marabou, Linson, and Alpha Beta Crown.
Yeah, they do have a comparison with Marabou. They do actually
comparing it with.
So I think in fact Crown has a comparison with Marabou. So
Crown has one.
Crown, which is another sort of paper that I will talk about, but Crown has a comparison with Marabou. I don't know if I have put it in the slides, but this is there in the papers. Let me maybe bring up that.
Wait a minute, you moved the slides too fast. We couldn't see anything.
Yeah, I'm just looking for a particular point to answer your
You're
question.
still searching, okay.
Yeah, so I think Yes, I've not mentioned that here, but Crown has a comparison with Marabu. So
Oh,
just
Crown has a comparison with DeepPoly.
with Marabu, not DeepPoly.
Marabou.
Yeah.
I guess Linson with DeepPoly always does better, no? No, I mean maybe
Yeah,
not.
Linson again. Linson is
Comes
going
up with
to
bounds, and therefore
yeah.
it
I
is
don't.
more.
Yeah, it'll have better bounds. So it'll very much do better than DeepPoly in terms of percentage verified, but it also takes a lot more time because those better bounds, they're using some SAT solvers to calculate them. But can you see these charts? So
Yes.
this is for Crown. So Crown is again very similar technique. They have slightly different tweaks on exactly how to calculate the bounds across ReLU, but we can sort of consider them to be sort of very similar techniques for our discussion currently. And the point that I want to make is that if you compare against ReLUplex, which is this is the bar, right? So
No, you have to explain these colors. What are those colors?
yes. So the red and yellow are basically two variants of Crown, which is close to DeepPoly, let's say, for our discussion. Then the blue and green are actually two variants of this FastLin tool, which is the other tool that was there over here.
Okay.
Yes, this
Is
is
FastLin also meant to be used for DNN?
Yeah. So this is FastLin is again another polytope based abstract interpretation kind of tool. And then there is an LP relaxation that they do. LP relaxation is based on what Planet. There's a paper called Planet which proposes another sort of approach, which I'll maybe not go into the details of that. But so there is another some other tool, and then this blue line is ReLUplex.
ReLUplex.
Yeah. So now.
Yeah, but they have not compared with Marabou with the node merging.
No, they have not compared with that. But if we compare it with ReLUplex itself,
it's much better.
Yeah, so it's not very clear whether it's better or not, because see here.
No. I don't know what they are measuring here. The time, or they say this.
So they're measuring
something. They say, I don't know what that means.
Yeah. So they're measuring two things parallelly. So one is that how much epsilon perturbation where each one of these tools be able to verify. That's the distortion.
Goes up a little bit and then comes down. What are those black points?
So those black points, the time.
Oh, the time.
Yeah,
and the bar graphs
are the sort of amount of epsilon perturbation that was able to be verified on the same network.
Oh.
So the more epsilon perturbation you can verify, the more accurate your technique is, because that would imply that you're able to, if you're not able to verify a certain amount of epsilon perturbation, that means that you're over approximating too much. So of course, all the abstract interpretation based techniques are, relatively speaking, over approximate, and Marabu does, or ReLUplex does much better in that respect. But again, if you look at the time is in log scale, and whereas these abstract interpretation based things, they take in log scale order 0 time, whereas ReLUplex takes some order 6, 7 sort of time. So it's like several orders of magnitude slower than any of these abstract interpretation based techniques. So yeah, so the accuracy, if you think about, accuracy is a loaded term, but let's say distortion, if we use their terminology, it goes up from 0.03 to 0.08. And what you know with ReLUplex is that 0.08 is the maximum distortion that is achievable. But to be able to verify that distortion, you're spending significantly more time. Right? So this is the sort of, Yeah.
So it's kind of, the import is clear now. So because ReLUplex is able to verify much finer properties, okay?
Yeah.
For smaller, it's more precise, yes. And that's not surprising because it doesn't use, it doesn't use as coarse and it doesn't use abstraction, as a matter of fact, okay?
Yeah.
So,
Yeah, and they do mention in their appendix, they have more comparisons where they mention that for a large number of the networks, they were not even able to get bounds from ReluPlex, because I think they have some table up here in the appendix. But anyway, they mentioned here that for a large number of networks, they're not able to get bounds from ReluPlex simply because ReluPlex just timed out and all of that, right? So they didn't even mention that those in the tables. So it's
That's
only
right.
for
ReluPlex, by the way, ReluPlex doesn't, it only works for Relu activation function, huh?
yes. So they were only comparing on Relu networks for these figures. They compare on non-Relu things with the other abstract interpretation based techniques. Yeah, so this is the sort of idea here. And yeah, so one more point I have regarding deep poly experiments, and then I think I'll stop. Oh, I do have 5 more minutes. Okay. So yeah, for convolution, it's also sort of the similar thing, but it's closer. It's closer in the sense that the accuracy is only slightly more, but the time taken is actually turns out to be more than the deep sea. And it turns out that the deep sea, is still the runner-up. And the idea is that it's slightly more accurate and takes slightly more time than deep sea for convolutional networks. For fully connected networks, it blows it out of the water essentially. But yeah. So I want to make one point, which is that these are really, really old experiments. One should not take these experiments to understand the state of the alpha beta crown tool, because beyond deep poly and crown and all of that, a significant amount of work, both in terms of techniques and I'm sure in terms of engineering, has gone into alpha beta crown, which means that alpha beta crown is right now significantly faster than the times we were seeing here with deep poly and crown and so
Yeah,
on.
which means that alpha beta crown is more state-of-the-art tool when compared to deep poly, correct?
Yeah,
Is that
correct. Yeah, that is what I mean. So that one should always keep in mind when reading these experiments, which is that this does not reflect the state of the art in any way. It is much more sort of a reflection of why people chose to explode in certain directions, because at that point experiments were showing that there is promise in such direction, right? So it is more about what established the technique at that point.
correct? So briefly, I want to mention, see, the VNN comp, by the way, VNN comp is a competition, by the way, that is done. All the tools, you can enter tools into this competition, and they give you a bunch of benchmarks, and those benchmarks are upgraded. This is serious competition. They give you winners get gold, silver, and bronze medals every year, and it's conducted every year, and these are mostly DNN, various different variants of DNN that you can enter your favorite tool and then compete and then win. Yeah. So that's serious competition. Yeah. I guess so. Verification, yeah. Neural network verification competition.
Yeah, so
Yes.
verified neural networks. So yeah, the fee is in
There's
the.
SP comp, there is hardware comp, there is all kinds of comps.
There is even a SAT-SMT competition, right?
Yeah.
I think, yeah.
Yeah, one thing that was not clear, but probably Jessica, in your presentation you will do, we are not covering convolutional network. I'm putting pressure on Jessica because, no. I'm saying convolutional, what is CNN? Why, mostly we are doing DNN now. And then only this class of properties, which either tell you robustness properties or something which says, oh, the output should be within certain bounds and those kinds of things. How is CNN structurally different than normal DNN? And why verification? What are the kinds of properties that you need to verify, and why those properties are more different and more complex? Those are the kinds of things that we brought up, and that's only going to be the. Okay, I think there. Can you do me a favor? Tell them that I'm coming. Okay, so thank you. Yeah.
Yeah. I
Thank
think
you,
I'll stop at this point. Yeah, I had a few more slides on crown, but I think we can skip that.
No. You could summarize in your next class, okay, and then you can mention that.
Sure,
yeah?
sure. I'll do that. Yeah. Okay, thanks.